Okay. We are, hey, what unit, do you remember what chapters we're just kind of finishing up? Yeah, 7 and 8. So what chapter are we starting? 3. Yeah, we're starting chapter 3 right now. Oh, I'm sorry, Mac. Yeah.
Is this our last unit?
Yeah, this is our last unit.
Yes.
Yep.
Yes.
So how much time, did anybody tell you how much time we have left in the semester? Including today, 17. Yeah, we've got 17 classes left. Now, that doesn't mean 17 classes for new information, because we are kind of required by the administration in our building to take 4 at least days at the end of the semester to review. So we really only have 13, maybe 12 classes because we're doing the test tomorrow, right? So I don't know, let's call it 11 classes to do this unit. So it's gonna go by relatively quickly, if that's okay with you. It's fairly straightforward. There is, for those of you who hate math, I don't know why you would ever hate math, but that's fine, that's okay. For those of you who hate math, there's very, very little math. The maximum amount of math you need to be able to do is like comparing 112 to 80. Do you know what I mean? Like comparing the relative size. Which one is bigger, 112 or 80? Right? That's the most math you really need to be able to do. Or let's take 1.2, or sorry, let's take 3.2 and subtract 1.2, so you get 2. Right? That's the kind of math we're talking about in this unit. It's not, there's no more unit analysis. We are done unit analysis until we review all of the other stuff at the end of the semester. Idris.
You should have done this at the beginning of the semester.
I somewhat agree with you. There's a reason why your textbook, which is a very good resource by the way, there's a good reason for them putting it before everything else. We're going to tie this information into some concepts that we've learned about earlier on in the semester. For example, do you remember all the way back into September when we were talking about gases? And we were talking about the difference between real and ideal gases. Real gases are attracted to each other. So they have, if you had a real gas and an ideal gas, one of those containers would have a higher pressure because the real gas, all of the real gases are attracted to each other, so they put less pressure on the walls of the container, so they occupy less volume. So we're gonna bring that idea, and we're gonna talk about why that is. We're gonna explain fully and completely why those real gases behave the way they behave. In order to do that, we need to talk about what the hell is a chemical bond. A chemical bond is an electrostatic interaction. It's an attraction between positives and negatives. Let's see. If you wanted this positive to be attracted to that positive, normally do positives, are they attracted to each other? No, hell no. No, they're not even close to being attracted to each other. They repel each other, right? So how could we get these positives to be attracted to each other?
Add a negative.
Change one of them into a negative. No, we could put a negative in the middle. Would you agree that if we put a negative in the middle, this thing's attracted to that, this thing's attracted to that, and they should get relatively close together? Does that make sense? Now, I totally agree with you. This positive and that positive still repel each other. So there's a very fine line of they're going to get close to each other, but at some point in time, if they get too close, they'll actually repel each other. Okay? So there's like a happy medium. There's a happy medium of how close these positives want to get to each other. This is the entire point. This is the whole purpose of a chemical bond. let's take a look at two atoms. Yeah, sure. What's the simplest atom you can think of? Simplest element you can think of? Oh, okay. H2O is pretty complicated, actually. What's the simplest single atom? A hydrogen atom. Let's look at a hydrogen atom. I'm going to draw a hydrogen atom, and this goes back to what we were learning about in our acids and bases. A single hydrogen atom has a positive in the center. Its nucleus is positive. And what does it have orbiting its nucleus? A single electron, right? And then let's add another hydrogen in here. So we've got two hydrogen atoms. Now, when hydrogen is an element, what's the formula for hydrogen? H2. So these hydrogens, they will naturally bond together with each other. And so what's going to help draw these two nuclei together? The nuclei of these atoms, they don't want to be together. What's going to help draw them together? The negatives. What do we call these particular negatives? What do we call these negatives that orbit around the nucleus? Electrons, right? These electrons, come on. Whoa, that's not good. These electrons, they form the basis. Ungroup. These electrons, they form the basis of the interaction between these nuclei. The only way we can get these nuclei to get close to each other is if we have these things come join these things. So we've got two negatives in here, and they're drawing these positives together. So this is the entire purpose of a chemical bond. These two electrons electrically glue these two nuclei together. What?
How come the negatives don't repel each other?
Oh, the negatives totally do repel each other. Okay? So here's the problem, is that this is just a model for our understanding. I wholeheartedly agree with you, Aaliyah, is that these negatives, under every other circumstance in the entire universe, they would love to be as far away from each other as possible, right? Yeah. But there's a happy medium where there's like a natural low point in the potential energy of this system where if this one's close to this and this one's close to that, then they don't mind being in the middle, because if we push them further apart, what happens to this negative if we push it further apart? It gets further apart from the positives as well. Does that kind of make sense? So there's just
that. The physics stuff?
Pardon?
Is that kind of like in physics? I don't know. Okay.
Yes.
I get it then.
Yeah, okay. All right, good. Good talk. Chemical reactions depend on, should say on. I don't know why it says of. Should say on an atom's valence electrons. So we're going to need to know this term about valence electrons. Do you remember what the hell a valence electron is? Did we talk about valence electrons at the beginning of the year? Woo. Yes, it's the outside electrons. Good, lovely. And then an orbital, we're going to have to understand what an orbital is. It's just a region around the nucleus where electrons may exist. And that's that orbital that I've drawn there. Electrons can exist in this orbital. Good, okay, awesome. So answer the following questions about the energy level diagram below. This is just, I just want to talk about this because we did review this in the beginning of the semester. Go ahead and answer these 3 questions. Talk to your friends if you need to. Idris, you were so good, and now you're fast. Exactly. Oh man, your mind has just withered away. You just blame it on the study exam. Yeah.
That's okay.
What?
8 electrons?
First it goes to 2,
8
and it's
electrons.
just, and you lost 6, so where's the 6? Yeah. Because, no, 6 there. Oxygen.
Argon 8, right?
Yeah, that's it. Wasn't it like 2 and 6?
That might be really wrong.
Yeah, I remember.
But it is.
The first one was 2.
Oh, that's what it was.
I don't know.
I did a hard
And then
way.
it goes to. What was your levels again? I don't know. 2.
I'm gonna give you 10 seconds to finish up your fantastic conversations, or finish up looking at your Instagram posts or whatever. Maya, is there anything good on Instagram? Is that what you're looking at right now? No? Right. Oh, okay. Surely for a school project. Yeah. Okay, let's try this. Answer the following questions about the energy level diagram below. Let's look at this. This is my energy level diagram. So the obvious first question, maybe it's obvious, I don't know. The obvious first question is, what element is this?
Oxygen.
Are we okay with that? It is oxygen, right? How do you know that it's oxygen?
8 protons.
8 protons. This is the atomic number, right? So the number of protons is the atomic number of that substance. So it is oxygen. How many valence electrons? Let's really quickly describe the term valence. What does valence mean? Outer shell. It's the most outside shell. Not the most outside shell there could be. It's the most outside shell that is occupied. It has to have at least one electron in it. So how many valence electrons does this thing have?
6.
It has 6 electrons. Why does it have 6 and not 8? Oh, okay. There's lots of different ways to answer this question, right? It's not 8 because these 2 electrons are in a lower energy level, correct? They are held closer to the nucleus, so they're not in the same energy level as the outside ones. It's also not 8 because it's not an ion. If this was an ion, then it would have 8 electrons in its outer energy level. Good. What is the energy level that's occupied by this valence electron? This is really easy. Are the valence shell, is it the first energy level?
No.
No, it's the second energy level. That's all you had to say. It's the second energy level. Okay, all right, that's fine. So now I want you to do some work for me. Is that okay? No. Can you write out, and you can do this a couple different ways, right? You can draw the actual Bohr diagram, or you can draw the shorthand diagram. Do you remember what I'm talking about? Either the circles or the really shorthand diagram. You have to include the number of protons and you have to include the number of electrons, but I don't really care about the neutrons right now. Yeah.
I have this so far, but I'm not.
Uh-oh. So how many protons?
It's not.
And how many is it now? So should it have the same number of protons or should it have a different number? You got 11 protons and how many electrons? that's talking about an ion. That's really important. Oh no, it means right? Yeah, it's your notes, man. Really? Oh.
Wait,
Okay. Before we move on, there's a really important distinction that we need to make, isn't there, Kylan?
yes.
Yes. The distinction is between atoms and ions. Now, Kylan, who should I pick on right now? What?
Me.
Oh, okay, I'll pick on you, sure. What's the difference between an atom and an ion?
Ions have a charge. Atoms don't. Are neutral.
Good. What that means, atoms, because they have no charge, atoms do not have a charge, the number of protons has to equal the number of electrons and vice versa, right? The positives have to cancel out with the negatives. Does that have to happen with an ion? No, in fact, that can't happen with an ion, right? You do not want the same number of protons as you have number of electrons. So let's do the sodium atom. How many protons does sodium have? 11 protons. Now, can an atom lose protons? No, not in a chemical reaction. It can in a nuclear reaction, but not in a chemical reaction. So we've got 11 protons. Okay, since we're an atom, how many electrons do we have to have? 11. So how many can fit in the first? How many can fit in the second? How many can fit in the third? 8. But do we have 8 left over? No, we've got 1 left over. Good. Now this sodium ion, what kind of an ion charge does it have? +1. So that means, did we gain an electron or did we lose an electron if we are positive? We lost a negative to become positive, right? So what that means is we've got 11 protons, 2 electrons, 8 electrons, and we're done. Does it make sense that when atoms turn into ions, what's the only energy level that's affected? The valence electrons, right? The valence shell is the only shell that's affected, right? Did these 2 electrons in here, did they get affected? Nah, no, nothing, right? These 8, did they get affected? No, they're not the valence shell, so no, they didn't get affected, right? It's only the valence electrons that we care about in a chemical reaction. Fluorine atom, how many protons in a fluorine atom? So we got 2 electrons. It's an atom, so we need 9, so we got 7. Let's think about this. Fluorine, is it gonna gain 1 or lose 7?
Gain 1.
What's less energy? What's less work for this atom? Gaining 1 electron is going to be less work than losing 7. Now I'm curious, where did I get that information from? How did I know that it was either going to gain 1 or it was going to lose 7? Okay, there's 2 different answers. That was a good answer, and that was a good answer as well. But Aaliyah, because you put up your hand, talk to me.
Oh, I was gonna actually continue what you were gonna say because maybe it was.
All right, Shahad, what did you say to me?
The charge on the relative of
On the ion, right?
Yes.
Yeah, the fluorine ion is -1, isn't it? So we know it's either going to gain 1 or it's going to lose 1, right? But then what else, Cassidy? What did you say?
If you look at how much the valence shell can be filled up, so if it's easier to gain or to lose, it basically just kind of look.
Good, yeah. So if we look at that valence shell and we look at the maximum occupancy, how many electrons can fit in there when it's full, well, that will tell us which one is going to be easier to do. We can either gain 1 to reach our maximum occupancy of 8 electrons, or we can lose 7. Now, do you think it's more likely that an atom will gain 1 or lose 7 electrons? Yeah, gain 1. Do you remember, I don't know how much we really stressed this at the beginning of the semester, but atoms, when they turn into ions, they like to have the same electronic structure as their closest noble gas. Do you remember talking about that? So they like to obtain the same structure or the same arrangement of electrons as whatever noble gas is closest to them. So if it's oxygen, that's neon. But if it's sodium, sodium is element number 11. It's only 1 past neon, right? It's still neon as well. So just a heads up, just a reminder that that's the case. So this thing has 9 protons, 2 electrons, and 8 electrons for a total charge of -1. Good. Okay. We're going to think about our orbitals, and this is really not anything new. Surrounding every atom in each valence shell, there's a certain number of orbitals. Now, an orbital is just, it's a little pocket where electrons like to congregate. Now, electrons don't like to do anything. They don't have personalities, but it just happens that they have their lowest energy in these pockets of area. Okay? So the first energy level has room for 1 orbital. How many electrons can fit in the first energy level? 2. And it just so happens that that's 1 orbital. Okay? So hydrogen only has 1 orbital. There can be 0 to 2 electrons per orbital. You can have 1 electron in an orbital. You can have 0, or you can have 2. You cannot have more than 2 electrons in an orbital. Have you ever seen us draw the diagram of, for example, let's draw oxygen just because we can. So we're going to draw nitrogen because it's different. When we look at nitrogen, nitrogen has an atomic number of what? 7, right? So we can fit 2 in the first orbital. And those 2 electrons like to congregate in what we call an orbital. I should be discriminating between the term orbital and energy level. How many electrons can we fit in the second energy level? We can fit 8, but how many do we have left over? 5. Have you ever seen us do this? 1, 2, 3, 4, and then what do we do with that 5th electron? Good. These are the orbitals. These are our 4 orbitals. Those are the spots where electrons can congregate. And it has to do with the size of the element, but also has to do with which energy level. How far away from the center of the element is it? Above the first energy level, there can be 4 orbitals, or 2 each, right? 2 electrons in each, right? So can you see how we've got our 4 orbitals here? Some of them, this orbital has 2 electrons, but what about these orbitals? How many electrons do they have in them?
1.
Just 1. And is it conceivable that some of these, if we had fewer electrons, maybe some of these would have none in them? Yeah, that's fine. That's all that says. Electrons like to spread out. They repel each other and fill up empty orbitals before pairing up. That's why I went 1, 2, 3, 4. And once I had half filled all 4, what was my only option? Start pairing them up, right? That's the only other option. Good. So that's the idea behind that. A bonding electron is a single electron in an orbital that could be shared with another atom. And a lone pair is 2 non-bonding electrons occupying the same orbital. I just got to take, yeah, that's where we're going. Good. Okay. So let's draw the Bohr diagram. We're not going to draw the shorthand. We're going to draw the circles and everything like that. Let's draw the Bohr diagram for beryllium, and then let's draw the Bohr diagram for fluorine. Okay. So over here is going to be beryllium, and over here is going to be fluorine. I don't know why I said Fe. How many protons does beryllium have? 4. So how many electrons can it have? It can have 4. So how many can we put in the first energy level? 2. So 1, 2. And because we're done, remember there's only one orbital in the first energy level. We have to fill it up before we can move on to anything else. Idris.
Is it okay if you put one of the dots on top and one of the...
That's fine. I'm honestly okay with that. Because that's something that historically we've done. Just as long as you understand that you can only do that for the first energy level, right? Okay, so how many electrons do we have left over? We got 2. So it doesn't matter where you start from. Typically we go top and then we go clockwise. So we got 1 here and 1 here. So I'm curious, in our valence shell only, how many bonding electrons are in our valence shell here? Look at our valence shell and read the description of a bonding electron. A single electron that's not paired up with any other electrons.
2.
So how many bonding electrons do we have? 2. Good. This is a bonding electron, that's a bonding electron. What that means is that if beryllium has an extra electron, and then another element has an extra electron, those electrons can combine and occupy the same orbital. Okay? So another element could come by, any element at all, as long as it's got one bonding electron. And this thing could come by and it could bond, and all of a sudden it could fill up that orbital. Does that make sense? It's one unpaired electron is available. Here, I'll share this electron with you if you share your electron with me, and then we're both happy, that kind of thing. So as long as you understand that right now. How many lone pairs does the valence shell have here?
2.
Isn't it 0?
There was a word that I used, right, Cassidy? That was really important there. This does not have necessarily a lone pair. I get it. This would be considered a lone pair if it was in the valence shell. Is it in the valence shell? No. How many paired electrons do we have in the valence shell? None. There are no lone pairs here. Let's draw fluorine. How many protons does fluorine have? 9. So we need 9 electrons. 1, 2, 3, 4, 5, 6, 7. So I'm curious, how many bonding electrons does fluorine have?
3.
Read the description of what a bonding electron is. It's 1, right? How many single electrons in an orbital that is half filled, right? I only see, oh, damn it. I screwed that up, didn't I?
Yes.
1, 2, 3, 4, 5, 6, 7,
Two more.
8, 9. That's my fault, Cassidy. I don't know how to count. That's ultimately always my problem. All right. So now we'll ask this again, Cassidy, because that's my fault. How many bonding electrons does this have? It's got 1 bonding electron. Good. Fantastic. It's got a single bonding electron. How many lone pairs does this have? It's got 3 lone pairs. Can you identify the pairs of electrons in the valence shell that are totally full? 1, 2, 3. Perfect. So these are lone pairs. These lone pairs don't contribute to bonding at all. They are not available for bonding because, remember, a bond is electrons that are being shared by 2 nuclei, right? And we can't share these 2 electrons. It's just not going to happen. Perfect. Any questions? Can we move on? Okay, we're going to do the structures. Yeah, we can do this. No problem. We're going to have to stretch this out a little bit more on Wednesday, but we can at least introduce it. Okay. A Lewis symbol is the greatest thing in the entire world because it's a shortcut. And chemists are notoriously lazy, not dumb. No, we're lazy, okay? So we are lazy, and so we want to take as many shortcuts as possible. A Lewis symbol is a symbol that contains dots just to show how atoms bond. I'll give you a little bit more information. All it is we're showing the valence electrons. So a guy, I don't know what his first name, but last name Lewis, whatever, doesn't really matter. He came up with this description of how to show you really quickly how things bond together. So let's take a look at hydrogen. How many protons does hydrogen have? 1. So that means how many electrons can a hydrogen atom have? 1, right? Here's how easy it is. You put the symbol in the middle, and because it's got 1 electron, no circles, no orbitals, no nothing. All we care about is showing the valence electrons. Now, let's take a look at this. The elemental symbol represents the nucleus and the filled energy levels, okay? So basically what we're trying to say is by writing this H here, that's everything that's inside of the valence electrons. Anything closer to the center than the valence electron, we don't care about. We don't care about how many protons are here. We don't care about how many energy levels are filled. We don't care about how many electrons other than the valence shell. Because what's the only thing that reacts in a chemical reaction? The valence shell of electrons. You either gain or lose valence electrons. That's it. That's all we care about. Okay. Dots represent valence electrons. Start by putting a single dot in each of the 4 orbitals where there's more than 4 valence electrons. Pair up the dots. Let's do an oxygen atom. So we could do a Bohr or an energy level diagram about this. How many protons does oxygen have? Good. Oxygen has 8 electrons. Sorry, 8 protons. So we can fit 2 in the first, 6 in the second, The Lewis formula for this is so easy. What's the symbol? What's the symbol for? Yeah, it's an O. You had your brain on the last problem. That's okay. That's it. That's it for this for the center at least. Now, how many valence electrons does oxygen have? 6. 1, 2, 3, 4, 5, 6. Done. Swish. Done. This whole thing all of this information is represented by the symbol, and these are represented by the dots. So it's still containing all the information that we need. Now there's a super easy, quick way to do this. Look at oxygen and tell me, how many elements do you have to count from left to right to reach oxygen? What row is oxygen in? Is it the first row, or is it the second row, or the third row? It's in the second row. So let's start at the beginning of the second row. How many electrons do you have to count? How many elements do you have to count over?
5.
So,
The 6.
okay, so 1, 2, 3, 4, 5, 6. Oh, how many valence electrons does oxygen have?
6.
Oh my,
Are we okay with that?
no.
No? Okay, well let's do more work then.
No. That was just my
Let's look at an oxygen atom. Look at oxygen. Where is, or ion, thank you. Where is the closest noble gas? Is it closer to helium, which is element number 2, or is it closer to neon, which is element number 10? It's closer to neon, right? Well, really, what that means is that its Lewis formula is going to look like this. Do you agree it's gonna gain 2 electrons, right? Let's prove to ourselves that that would actually work. An oxygen ion is O2 minus. So did it gain or lose electrons? It gained, right? Electrons are negative. So an oxygen ion, 8 protons, 2 electrons, 8 electrons, good, lovely. We're going to do one last one. Okay? One last one. Let's do a neon atom. Which row is neon in?
2.
It's in the second row. How many elements do you have to count to go all the way to get to neon?
8.
So how many valence electrons does it have? As an atom, it's got 8. Perfect. No problem. How many bonding electrons does neon have? How many bonding electrons does neon have? How many single electrons all by themselves does neon have? 0. So how many bonds can neon form? None. It can't. It can't form any bonds. This is why the noble gases don't react with anything. We'll talk about this more on Wednesday. See me at Flex or lunch or after school today or whatever if you have any questions at all about the test for tomorrow.